Okay. Lewis structures, one of the main downfalls of Lewis structures has to do with their two-dimensional. So okay, so Lewis structures are two-dimensional. vsepr structures are three-dimensional. vsepr structures also okay, so Lewis structures, the bond angle predictions are very poor, very inaccurate. Where vsepr, they're fairly accurate. Okay. Now, vsepr is what we're going to be doing today. There are two levels of complexity. We're doing the first level. When you get into 1A, you're going to go to the next level. But they're assuming that you know the first level already. Okay, central to vsepr is something called a central atom. Okay, a central atom is an atom that is bonded by two or more other atoms. So that means, thinking about the Lewis structures, hydrogen only has one bond. So it can't possibly be a central atom. All the halogens have one bond, so they can't have be a central atom. Only if you can have two or more bonds. Now, oxygen is capable of two bonds. So if it's two single bonds, it can be a central atom. But if it's a double bond, it can't be a central atom. So if we look at water and carbon dioxide. Over here, this oxygen on your left qualifies as a central atom because it's got two hydrogens coming off of it. The carbon dioxide oxygens only have one atom bonding. So these are not. So in this case, the only one that's a central atom will be the carbon. Carbon's got the two bonds. Okay. So if a structure has multiple central atoms, you have to do multiple analyses per central atom. Okay, let's look at this as acetic acid. So how many central atoms are there? Here we have two, we have three. Okay, so let's look at that carbon there. Is that a central atom? It is, because there are four bonds coming out of that carbon. What about that carbon? It has three. What about this oxygen? That is qualified to be a central atom? No, because it only has one bond, a double bond, one bond come down to that carbon. So that's not a central atom. What about this oxygen here? Yeah, because that oxygen has two bonds. The hydrogens, by definition, can never be a central atom because they can only have one bond. So we have to do, for this molecule, we have to do three analyses. For carbon on the left, carbon in the middle, and the oxygen on the right. Okay, there are two analyses that need to be done. Okay. From the Lewis structure, determine the number of electron groups. Okay, there are three or four forms of electron groups. That's a single bond, a double bond, a triple bond, and a non-bonding electron pair. So you got four types of electron groups. Many people think a double bond is two electron groups. It's one electron group. A triple bond is not three, it's one electron group. It's six electrons, three bonds, but it's one electron group. Same with a double bond. Four electrons, one electron group. An electron pair, even though there's nothing attached to it, is an electron group. Okay, so that's step number one. Now, let me give you an example of determining that. Well, let's use carbon dioxide. Okay, we already know that the oxygens are not central atoms. The only one is the carbon in the middle. So how many electron groups does that carbon have associated with it? Two. Okay. So two electron groups. Hello. All right. Now, yeah, you say dim it in the back. Maybe I should use a different color writing too. Let me change color also with the. Okay, when you have two electron groups, you have linear electron geometry. Just the way that carbon dioxide looks. It's linear, okay? Okay, let's look at this guy. How many central atoms are there? One, that carbon in the middle. Oh, one other thing. Let me make sure this is focused also. All right, so let's analyze that carbon in the middle. Okay, how many electron groups are there surrounding that carbon? We have 3, 2, 4. No one's going to say 6. It's 3. Okay, so we have, yeah, remember up here? I said these all qualify as one electron group, single, double, triple, or. Okay, so we have oops. So those are the 3 electron groups. If you have 3 electron groups, you have trigonal planar. What does the word planar mean? Yeah, so how would you, on the plane? Flat. Yeah. In other words, 2-dimensional, not 3. Okay, so CH4, how many electron groups do we have? 4 electron groups. Now this is 3D. This is a tetrahedral. Okay, tetra is 4, hedral sides, 4-sided, looks like a pyramid basically. 4-sided pyramid. Okay, so we have 3 kinds of electronic geometry: linear, trigonal, planar. Trigonal, remembers 3, flat, linear, trigonal, planar, and tetrahedral. So when you're doing your dry lab, step number 1 is do the Lewis structure. Don't do anything with S's in it. There's an SO2 and an SO3 in there. I believe an SO4. Don't do those. The reason is this sulfur can have more than an octet. So it kind of messes up the formula. You're going to get into that in 1A, those exceptions. But for our class, don't do anything with sulfur in it. Okay, then the next thing you need to do is figure out the electronic geometry, which is what we just did. Count the number of groups. Now, let me do one more. And let's do water. How many electron groups does water have? We have 2. We have 4. Remember now, we count single bonds, double bonds, triple bonds, and non-bonding pairs. So water has that oxygen there with two pairs that aren't being bonded. So this has four groups. So what's the structure of water? The electronic structure. It has four electron groups, tetrahedral. And does that look like a pyramid to you? Doesn't look like a pyramid to me. Okay, but it's the way the electron groups are set up. The electron groups are set up in a tetrahedral. There's nothing attached to the two lone pairs. So when we look at this first level of organization, you can take your fingers and you're going to cover the atoms. You're just looking at the bonds, the electron groups. No attached to atoms. So really, that's the part of water we're looking at. No hydrogens attached. Okay, so this has four groups, hence those groups are arranged in a tetrahedral geometry. Okay, so again, electron groups are single, double, triple, non-bonding pairs. And the reason why I keep repeating this is that is a very common mistake when people do vsepr analysis. Okay, so that's the first step. The next thing we need to do is figure out what's bonding and what's non-bonding. What's bonding means it's attached to an atom or bonded to an atom. Now I'm talking about the electron group. Electron group is attached or bonded to an atom. Non-bonding means the electron pair okay, when we break it down to bonding and non-bonding, that's the way we can determine what the molecular geometry looks like. So we have two kinds of geometry. The electronic geometry, which is the geometry of how the electron groups are spaced out relative to one another. The non-bonding ones and bonding ones determine what the thing would look like if we had a magnifying glass or a microscope looking at it. So if electronic geometry okay, so if we have electronic geometry of linear, then the molecular geometry is also linear. Okay, so that's an easy one. Linear, linear. Okay, if the electronic geometry is trigonoplanar, we have two possibilities of molecular geometry. So if we have Okay, so if we have 3 bonding and 0 non-bonding, like our example here, the CF2, that guy here, okay, this molecular geometry is going to be the same as the electronic geometry, trigonoplanar. However, if we have something like okay, like that. Okay, in this case, we have 3 electronic groups. That means the electronic geometry is trigonoplanar, but we have 2 bonding, 1 non-bonding. That means the molecular geometry is bent. So it sort of looks like water, bent. Now, if the non-bonding is 0, then the electronic geometry and the molecular geometry are the same. Okay, so if non-bonding is 0, in other words, there's no lone pairs involved in electronic groups, it's the same. If you do have non-bonding pairs, then the geometry is not the same. So if we have 4 electron groups, that means the electronic geometry is going to be tetrahedral. And we have 3 options now. We have 4 bonding, 0 non-bonding. And remember, if it's 0 non-bonding, then the electronic and the molecular geometries are the same. So this would be tetrahedral. If we have 3 bonding, 1 non-bonding, we have 3 bonding, 1 non-bonding, like ammonia. This is going to be no, trigonal pyramidal. So it's sort of going to look like a pyramid, except it's going to have 3 sides rather than 4 sides. And then if we have 2 bonding, 2 non-bonding, we have bent again. And a good example of that is good old water. And remember, this is per central atom. So like I showed you up above with acetic acid, there are 3 central atoms, 3 analyses. That means there's 3 electronic geometries and 3 molecular geometries, 1 per central atom. Now you have your lab packet. I just need the first page. Okay, you're going to be talking about vsepr class. You're also going to be talking about bond angles. So let's talk about the bond angles first. What do you think the bond angle for linear is? What would that angle be? 180. So for linear, it's going to be 180 degrees. Okay, what do you think this bond angle is? .360 divided by 3 is 120, right? Now, these angles I'm giving you assume, you get that word again, assume that the attached atoms are the same atom. If attached atoms are different atoms, they have different electronegativities, which is going to affect the bond angle. But we're going to work in a perfect world. Let me smile. Perfect world. And it's going to be 120. But just keep in mind, it's not that. It's going to be some distortion of that. In fact, there's a whole section in your book on bond distortion. So these are the ideal bond angles. Now, tetrahedral is not 90. It's because it's three-dimensional. If it was flat, it would be 90, but it's three-dimensional. So it's 109.5. For trigonopyramidal, because it's a tetrahedral, it's 109.5. But remember, it's distorted because of the non-bonding pair. It pushes those hydrogen legs closer together. So it's really less than 109. In fact, it's 107, actually. All right, if you have bent, it's even more than 109.5. So basically, the three angles you need to know is 180, 120, 109.5. And if all the attached atoms are the same, then those are the angles you'll end up with. Okay, in vsepr, the language of vsepr, we have something called a vsepr class. Okay, the A stands for the central atom, and there's X, and there's two of them, so that's X squared. that connotes actually, it's not X squared, it's a subscript 2. That means there are 2 bonds to that central atom. For trigonal planar, it's going to be a central atom, and we have 3 bonded atoms, X3. For bent, in terms of 3 electron groups, we have central atom, 2 bonded, and 1 non-bonding pair. So that's AX2E. For molecular geometry of tetrahedral, that's going to be AX4. For trigonal pyramidal, it's going to be AX3E. And for bent, it's going to be AX2E2. That's the vsepr class. So you can stick any central molecule in there for A, any atoms for E, actually any atoms for X, and the E is always going to be non-bonding pair. No exceptions there. And that's basically, after you do the Lewis structure, you analyze the molecule, and then you start looking at it in terms of vsepr. Okay, the electronic geometry, the molecular geometry, and the class. Also bonding angles. And that's what our dry lab is today. All right, so I'm waiting on time, 12:30. Okay, I wanted to cover the lab for you before you started your lab. Let's do some examples. Okay, before I do an example, are there any questions on these guys? You're probably not seen this before. If you read the lab, the dry lab, at least it kind of going, oh yeah, I remember reading about that. Oh, yeah. So, all right, so let's do some examples. I gotta come up with something here. What would be a good example? Okay, so that would be OF2. All right, so if electronic geometry, what would that be? How many electron groups? We have 4. That means the electronic geometry is going to be tetrahedral. Okay, how many bonding, how many non-bonding? 2, 2. Okay, the OF and the OF are bonding. The 2 electron pairs are non-bonding, so it's 2, 2. So So the molecular geometry is going to be bent. What's the angle? What is it again? Less than. Yeah. Okay, it's less than 109.5. For the lab, all they want you to do is they want you to put 109.5, but just remember, it's usually different than that. Okay. Oh, in the class. What? What do the arrows mean? Over here? We're talking about this arrow. And if there are two of them, that means less than instead of just one. Better? Okay. Oh, the class, yeah. What would it be? Hmm? Well, all of them have A in it, right? And go back to here. The bondings are going to be the X's and the non-bondings are going to be the E's. Right. AX2, E2. Exactly. Good. Now, I also have extra practice. If you look at the modeling lab file, this is what I just did. What's missing though is the vsepr class and the bonding angle. So the linear up here would be 180. The next two are going to be 120. The next three are going to be 109.5. But that's a nice, pretty picture of what I did. And I gave you lots of practice. For example, NF3. Okay, that's going to have 4 electronic groups or domains. Electronic geometry is going to be tetrahedral. bonding versus non-bonding, 3:1. That means it's going to be trigonal pyramidal. And then the angle is going to be 109.5. And the class would be AX3E. Lots of practice. Okay, so that's under files towards the bottom. So after you go through your dry lab and you want more practice, head over to Canvas files. Now, there's been Tyler DeWitt on YouTube is a real good tutorial. He's a blonde guy, talks fairly fast, but everything he does is almost exactly the way I teach. So you won't get confused if you look at a tutorial from him. Ignore the organic part. He has tutorials on physics, chemistry, all kinds of chemistry, math, etc. The organic chemistry tutor, his method is also very similar to mine. And GAG, Khan Academy, extremely comprehensive, but very boring. So just have lots of caffeine before you look at the Khan Academy. These are pretty good tutorials. I've been using, particularly Tyler DeWitt, I've been using him for 15 years or so. He has quite a few tutorials as well. I know a number of you have been asking about, besides your textbook, besides me, besides your study group partners, you'll find if you're in a study group, things go much, much better. And these guys can help. All right. There's been some questions about extra credit also. Okay, you have one shot at extra credit, and that will go against your lowest test grade. You get a 50% rebate. Well, say you got a 60. How many percentage points did you miss? 40. 50% rebate of 40 would be how much? 20. So you get 20 back. Excuse me. So 60 plus 20 is 80. So you turn your 60 into a B. And you can turn it in anytime you want. It's going to be two parts. One is a three-part poster. And then the other is a 1,000-word essay. Think of the poster as your multimedia part of your essay. And look through the examples I gave you under test-related files, test-related poster session. There's quite a plethora there of topics. They're very diverse. But most of you, for example, one young lady at Sac City this semester, she's in my OChem class, and her background is El Salvador. So I asked her, I said, and she's very short, she's 5'10". I said, does your village from where you came have cenotes? And she didn't know what a cenote was. And it's basically an underground cave. And whenever you have underground water around caves, it's got a ton of carbonates in it. Carbonates stunt your growth. And that's why most villagers around cenotes are very short. Like if you go to Cancun, they have a lot of cenotes there. And the people there are traditionally very short. You know, like guys will be 5'5", 5'4". Women will be, lower than that yet. So that's what she's going to do her poster on, her paper on, cenotes, and the chemistry of the carbonates and how that affects growth. So, I mean, you can put anything together that you're interested in it. I just want you to be interested in it because it's an opportunity in your schooling where you get to study something you're interested in and get points for it at the same time. Death of dying, a chemistry of dying, chemistry of depression. What about hormones? A lot on preservatives, a lot on pesticides. Who's heard of Manuka honey? Okay, what's good about Manuka honey? I mean, why is it so much more expensive than regular honey? That's right. It comes from New Zealand, and it's the pollen from the tea plant that grows in New Zealand. But it has very much higher medicinal properties than local honey. I've got one of my students did a project on that, and she worked as a CNN, and they specialized in burns. And I've got 3 pictures a month apart where that burn was treated with Manuka honey, and it's amazing the difference. You can buy gauze that's got Manuka honey in it. It's really cool stuff. It's not quite as sweet as regular honey, but we used to, my late wife, she had a lot of arthritis. I mean, really bad in her hands. And she would take the gauze at night sometimes and just put it over her arthritis, and it helped. It cut down the pain a lot. And it's got antibiotics in it. It's got hydrogen peroxide in it, all kinds of stuff. Pretty cool. I learned that from my student's poster. Didn't know that before that. Pretty cool. So I've been doing this for about 14 years, these posters. And certain classes, it's required. Other ones, it's optional. Like with you guys, it's optional. So with you guys, it's extra credit. In my OChem class, it's counts as a test. So yeah. Huh? Yeah, it's phonetic. Great stuff. Good point. You show it to me, no presentations. And then I ask you sometimes a few questions about it. And so also no paragraphs on your poster. I want bullet points. Now, if you roam around, the OChem class for allied health also does that. And she puts the posters up around the halls. So those posters you see around on the halls, most of them are on drugs. She might have required them to do something on drugs. That's a good start, just looking at some of those. She only puts ones up that she likes. That list I have some that are mediocre and some that are really good. But I'll give you an idea of what it's about. So if you're the least bit handy with arts and crafts, this is your opportunity to shine. I've had students put blinking neon lights on their poster, all kinds of stuff. And then there's a 1,000-word essay as well. That's a pretty short essay. Okay. All right. Yeah. No. Do it as an introduction to the topic as opposed to what you've learned. Okay, so